Hello everyone, welcome to week number 11, which is the penultimate week for this particular course. In the previous week we have talked about the properties of gas mixtures, where basically we talked about the mixture of non-condensable gaseous substances both in ideal and real sense, and we have seen how to calculate the properties of such kind of gas mixtures when the mixture is behaving like an ideal gas or when it is an amalgamation of several kind of real gases. In this week we are going to deal with the mixture of gases and vapors. That is, we are going to talk about the mixture where one or more components are condensable during a process, that is the one of the gaseous substance, though normally it may be under gaseous condition, but with change in the state, that is with decrease in the pressure or increase in the decrease in the temperature or increase in the pressure, it can undergo a condensation process, whereas some other components of the mixture may be a non-condensable gaseous substance. The most common example of that one can be the atmospheric air only, because you know that in atmospheric air we have several non-condensable gases like oxygen and nitrogen are the most prevalent one, but we can also have some quantity of carbon dioxide and a few very small quantity of noble gases or gases like helium or neons. However, in atmospheric air, though in very small quantity, but still we can have water vapor as well, and therefore, when you pick up a fixed mass of atmospheric air and subject that to some kind of cooling process, then while the non-condensable part will remain remain as it is, that is, I should say it should retain its gaseous phase. There will be only change in the temperature of that. Therefore, only the heat transfer that is taking place with that non-condensable part is only in sensible mode, but it is very much possible that the condensable part, that is the water vapor, may start to condense once the temperature drops below a certain value. And therefore, whenever you are dealing with a mixture like this gas and vapor mixture, just like the example of atmospheric air, we have to deal with several other parameters and their property estimation. Therefore, also we have to be very careful about the way we estimate their properties, because we just can't treat them similar to the mixture of gases which we have discussed in the previous week. So, this week we shall firstly be seeing different properties that we define for the gas vapor mixtures. Then we shall be seeing the ways to calculate those properties. Then I shall be introducing you to something known as a psychrometric chart, where we can represent different processes involving the gas vapor mixtures, and then we shall be seeing the application of this one in engineering sense. And what is the biggest application of gas vapor mixtures? Of course, in the field of air conditioning, because whenever we are talking about any air conditioning application, like the studio where I am sitting, here I have an air conditioning running, but the objective of this air conditioner is not to control the temperature alone, rather also to control the humidity or moisture content of this air, and therefore it is operating over the air that is covering the entire volume of this room, which has both the condensable and non-condensable part, and therefore it is dealing with a gas vapor mixture. Of course, the air conditioner itself, or inside the air conditioner, we have something very similar to a refrigeration system, that is, we are having some kind of refrigerant which is passing through a common vapor compression refrigeration system. There is condenser, there is evaporator, there is condenser, there is a compressor, and there is also an expansion valve. But the refrigerant is treating this particular room as its cooling chamber, from where it is going to pick up the heat in the evaporator, and while picking up the heat, it has to deal with a gas vapor mixture. Of course, the gas vapor mixture is not coming in direct contact with the refrigerant, but to what temperature we should set the refrigerant or we should set the evaporator, that is dependent on the properties of the gas vapor mixture. And therefore, we are going to take this atmospheric air as the biggest example of a gas vapor mixture, and whatever we are going to discuss in this week, we are going to consider only a mixture of water vapor and some non-condensable gases similar to air. However, I should clarify at the beginning itself, whatever we are discussing here, that is equally applicable to any other mixture of gas and vapor. Now, atmospheric air can be visualized to be or can be viewed to be a combination of two types of substances. So, if we write atmospheric air, we can see there is a part which is the non condensable one and there is a part which is water vapor. So, we have the water vapor part which is condensable and the remaining all the non condensables that we are going to club together into something conventionally called dry air, which is the combination of all the non condensable elements. The term dry air is used because if we remove the entire quantity of water vapor from the atmospheric air, the thing that is left that conventionally called dry. So, dry air is the part of the atmospheric air after removing the water vapor. It is a combination of non condensable gases and therefore, whenever you are treating any air conditioning process, then generally the quantity of dry air that remains constant. In fact, forget about the air conditioning application, even when we are talking about our open atmosphere, generally the quantity of dry air, that is the mass of non condensable present there, that does not vary by a very significant amount. There the variation can mostly be neglected. Whereas, the quantity of water vapor that keeps on changing throughout the day, throughout seasons, and also with the location that keeps on varying at a particular time as well. Therefore, the air water vapor part that keeps on varying and accordingly the water vapor plays a big role in deciding our comfort level. We know that when the water vapor or the moisture content in the air is too high, we feel quite uncomfortable, whereas when the moisture content is too low, then the air keeps on absorbing water vapor from our body, and that is may not be also the most comfortable situation for this. So, in a nutshell, the atmospheric air comprises of two parts, one is dry air whose mass generally remains constant, other is the water vapor whose mass keeps on changing. Now, in air conditioning application, generally we are concerned about the temperature range of minus 10 degrees C to 50 degrees C. So, we are always bothered about this particular temperature range, or we hardly go outside this particular temperature range minus 10 to 50 degrees Celsius. And within this particular temperature range, we can often treat this dry air part to be an ideal gas. So, here for our purpose, our discussion purpose, we are going to assume this dry air to be an ideal gas with constant specific heat of Cp equal to 1.005 kilojoule per kg Kelvin. This is not a bad assumption, because if you look at this particular table, here the magnitude of specific heat Cp for dry air is shown with temperature, and you can see as minus 10 to 50 degrees Celsius we move on, the change is quite small, it is changing in the third decimal place. That is over this 60 degree Celsius temperature range, the variation is only about plus minus 0.2%, and therefore, we generally going to stick to this particular value of 1.005 kilojoule per kg Kelvin, and we shall be treating this dry air part as an ideal gas with this constant specific heat. Therefore, the enthalpy for the dry air part, this symbol dA, this suffix we are going to use to denote dry air. So, dry air we shall be denoting with dA, whereas water vapor we shall be denoting with Wv. So, if we want to calculate the enthalpy for dry air at any particular temperature, we can often calculate this one as Cp into T minus T reference, and the common choice for reference temperature is equal to 0 degree Celsius, and therefore, we can easily write this one as Cp into T, where T is expressed in Celsius. This is an important term that you should remember. Here we are writing this T, though we are using capital T, which generally represents the absolute temperature. Here we are representing this T as this temperature written in Celsius, because our choice of T reference is equal to 0 degree Celsius, and therefore, the enthalpy for dry air can often be taken as 1.005 into T times this much of kilojoule per kg, and the change in enthalpy of this dry air, delta H dry air, therefore, can be written as Cp into delta T, that is 1.005 into the change in temperature, where delta T can be represented either in Celsius or in Kelvin. But if we want to use a British unit or FPS unit, the Cp has to be represented in APS terms. So, the dry air part is very easy to deal with. You can just visualize the dry air as an ideal gas, just like what we have done in the previous week while talking about the ideal gases, and we are here also we are going to treat this dry air as an ideal gas with a constant specific heat, which is 1.005 kilojoule per kg Kelvin. And just the way you have calculated enthalpy, similarly we can calculate other parameters also if required. But what about the water vapor part? Now, if we can deal with the water vapor as an ideal gas, that would have simplified our analysis quite a bit. And thankfully, below this 50 degree Celsius temperature range, we can actually consider or assume water vapor to be an ideal gas as well, without incurring too much of error, because the saturation temperature, saturation pressure for water vapor or water at 50 degree Celsius is 12.3 kilopascal. You know that when you are talking about water vapor at a temperature below this for this given pressure, or at a pressure above this for this given temperature, it will be in the superheated condition. At a, or I should say, I told wrongly, when you are talking about water vapor at this particular pressure and a temperature higher than 50 degree Celsius, or at 50 degree Celsius, but at a pressure lower than this, it will be superheated vapor. Now, from the property values, it has been seen that when the, as long as the pressure of water vapor remains below this 12.3 kilopascal, we can assume it to be an ideal gas with hardly any error, as we shall be seeing shortly, because within this zone we can safely use the relation PV equal to RT even for water vapor as well, and that simplifies our analysis quite a bit. We are going to treat this pressure or atmospheric air as a combination of two ideal gases. One is the dry air part, other is the water vapor part, and accordingly the total pressure can be represented as the summation of the partial pressure of the two components. One is the dry air part plus the water vapor part. So, the total atmospheric pressure is a summation of the partial pressures of dry air and water vapor, because we are assuming the dry air part and also the water vapor part as ideal gas. While it is not very surprising that the dry air is behaving like an ideal gas, but it may be a bit surprising with the water vapor, but that is actually a great relief to us, as we do not have to go to the tables to calculate the properties of water vapor. We can easily calculate this by assuming this to be an ideal gas. So, both the dry air part and water vapor part follows the ideal gas equation of state. Like if we take a certain volume of atmospheric air, often called the moist air, the dry air is without the water vapor, and when we mix water vapor with dry air, this mixture is often called the moist air. So, if we take a particular quantity of moist air and we measure the corresponding volume and the temperature of the moist air, then we can easily apply the ideal gas equation of state over the entire mixture. Like if we talk about the mixture, then if PM refers to if P refers to the total mass of pressure of the mixture and V is the volume, then this should be equal to N into R bar into T, whereas this is for the total mixture, that is total moist air. Similarly, for the dry air part, we can write the partial pressure into the total volume into the number of moles of this dry air into R bar into T, and similarly for the water vapor part, its partial pressure into V will be equal to number of moles of water vapor into R bar into T. So, we are going to treat both of them as an ideal gas as long as the water remains in the vapor state. Now, for water, how to calculate enthalpy, that we have seen here. What about the for dry air, we have seen this. What about the water vapor part? For the water vapor part also, we can go by a route something similar to this, or another thing is the help of the TS diagram that I have shown here. Of course, we are assuming water vapor to be an ideal gas, that means its enthalpy should be a function of only temperature, and thankfully that is what we can see here. See, several constant enthalpy lines are shown here, these pink lines, and in this superheated side below 50 degree Celsius, of course, that is below this particular temperature level, these lines are almost horizontal. That means this constant enthalpy lines also represents isothermal condition, and therefore, if we draw an isotherm which will be a horizontal line, this in the superheated zone both temperature and enthalpy remains constant along this line, and therefore, enthalpy for water vapor on the superheated side, say we want to get the enthalpy for this particular point, while the entropy changes along this isotherm or along this constant enthalpy line, but enthalpy does not change, and therefore, the enthalpy at this particular saturated vapor point can be easily be used for the value of enthalpy along any point in this line. And hence, we are going to take enthalpy for water vapor for a given temperature and low pressure, or I should say low value of this partial pressure of water vapor to be equal to, as per our notation, Hg corresponding to the temperature. This is, or I should not write equal to, this should be almost equal to or nearly equal to. So, we are going to directly take H for water vapor to be equal to Hg for that given temperature, but condition is temperature has to be lower than 50 degree Celsius, which is generally true for air conditioning application, and also the partial pressure for water vapor has to be low, which is also true, as we shall be seeing very shortly. And of course, we can also use the relation similar to the dry air part, that is generally Hg for water at vapor at 0 degree Celsius has got a value of 2500.9 kilojoule per kg, and Cp for water vapor over this entire range can be assumed to be constant over this range of -10 to 50 degree Celsius. It is 1.82 kilojoule per kg Kelvin. So, one option of taking the enthalpy for water vapor is equal to Hg for that given temperature. The second option is we can use these values of Cp and Hg at 0 degree Celsius, very similar to the way we have calculated for dry air. There we shall be writing H for water vapor is equal to Hg at 0 degree Celsius plus Cp for water vapor into T minus 0, that is 2500.9 plus 1.82 into T, where T again is Celsius, this much of kilojoule per kg. So, there are two ways we can calculate the enthalpy for water vapor. One is using the value of Cp, and other is to use the table and get the value of Hg corresponding to that temperature, because I repeat, with below this 50 degree Celsius constant enthalpy lines are also constant temperature lines, and therefore, enthalpy remains constant over this entire superheated zone, and hence we can take the value of Hg. If we compare these two approaches using this table, see if we take up say 20 degree Celsius. So, if we follow this approach, then this is the value. If we follow this approach, then this is the value. So, there is only 0.1 kilojoule per kg difference in absolute magnitude. Over this entire range, the maximum deviation is 0.6 kilojoule per kg or minus 0.6 kilojoule per kg, which is extremely small compared to the large numbers that we are talking about, and therefore, you can go by any one of the approaches. So, we have seen that now moist air is a combination of dry air and water vapor, both can be assumed to be ideal gas, and for both of them we now know how to estimate their enthalpies. Let us now move to some two terms which are very common, specific and relative humidity, or at least the term relative humidity must be well known to all of you, because whenever we hear any news bulletin or news bulletin about the local temperatures etc., they also keep on mentioning the relative humidity, and we also know that relative humidity high means it generally is very moist situation and may not be very comfortable situation. But what is the definition of relative humidity, that we shall be learning here, but before that this term specific humidity, or often called the absolute humidity or humidity ratio, that needs to be defined. So, we generally use a symbol omega to define the absolute humidity. The definition of absolute humidity is very simple. In a sample of moist air, absolute humidity or specific humidity or humidity ratio is just the ratio of the masses, mass of water vapor by mass of dry air. As I have mentioned that the quantity of dry air generally does not change during air conditioning application. So, quite often we represent different properties in terms of per unit mass of dry air. Like we shall shortly be seeing, the total enthalpy and a few other parameters are defined in terms of per unit mass of dry air. Very similarly, here the mass of water vapor is defined as per unit mass of dry air, and that is what we are calling the humidity ratio. Now, we know that both dry air and water vapor can be assumed to be ideal gases, and we can use the PV equal to nRT relation on this. So, for a given sample of volume V and temperature T, if we write them, I wrote in the previous slide also, but I am repeating here. For the dry air part, we can write P dry air into V to be equal to N dry air into R bar into T. Similarly, if we maybe we can write this one as mass of dry air into R for dry air into T. Similarly, P for water vapor into V will be equal to N for water vapor into R bar into T, that is equal to mass of water vapor into R for water vapor into T. So, taking the mass of water vapor from here, so in the numerator we have partial pressure of water vapor into V divided by R for water vapor into T. In the denominator, mass of dry air can be written as partial pressure for dry air into V divided by R for dry air into T. Separating out the terms, so we are left with now P for water vapor by P for dry air and R for dry air by R for water vapor. Now, R for water vapor is very well known. We can easily convert this relation in terms of molecular weight as well, because we know that for any substance R is given as R bar by molecular weight. So, if we convert in terms of that, partial pressure for water vapor by partial pressure for dry air can be converted into molecular weight of water vapor by molecular weight of dry air. Now, molecular weight for water vapor we easily know, which is actually about 18. Molecular weight for dry air, how can we calculate? In the previous week we have learned, if we assume water vapor to be comprising of say 79% by nitrogen and 21% oxygen on molar basis, then by using the mole fraction and the molecular weight of nitrogen and oxygen individually, we can get the apparent molecular weight for this. So, if you put that out, then you are going to get this ratio to be equal to 0.622, putting the values of this m molecular m for dry air and m for water vapor into partial pressure for water vapor by partial pressure of dry air. Now, we have also seen that as air is a combination of these two, so P is equal to total pressure, where P is total pressure is P water vapor plus P dry air. Therefore, P dry air, the denominator can be written as P minus P water vapor. So, replacing this, we are getting finally omega to be equal to 0.622 into P water vapor by P minus P water vapor. So, somehow if we have idea about the partial pressure of the water vapor, we can calculate the humidity ratio, or vice versa, if we know the specific humidity, we can calculate the partial pressure of the water vapor from the knowledge of the total pressure, atmospheric pressure, that is. Now, we have the relative humidity. Let us say we have a certain sample of air. We know the pressure and temperature for this one. So, we know the total pressure, we know the total temperature, and at a particular instant of time its specific humidity is omega 1. So, corresponding to this omega 1, we know that it has some mass of dry air and some quantity of water vapor, let us say W water vapor 1 for this. Now, we keep on adding more and more water vapor to this. The mass of dry air remains unchanged, but the mass of water vapor keeps on increasing, and as the mass of water vapor keeps on increasing, then specific humidity also keeps on increasing. But as specific humidity increases, then initially there will be no change in the total pressure or temperature of the system, or actually the pressure and temperature of the system will remain the same. But as the mass of water vapor is increasing, whereas the mass of dry air remains the same, then while omega is increasing, the partial pressure for the water vapor is also increasing, whereas the partial pressure corresponding to dry air keeps on decreasing, because total pressure and temperature remains the same. And if we keep on increasing the quantity of water vapor or the moisture content of this moist air, then you will reach a certain situation where the moist air can't take any more water vapor. I repeat, we shall finally be reaching a situation where the moist air will not be able to take any more water vapor. then we call that the moist air or that atmospheric air has become saturated with the water vapor. In that condition, under the saturated condition, whatever partial pressure of water vapor that we have, let us say we call that should be the maximum partial pressure. Let us say we call this PWV max, that is the maximum partial pressure of the water vapor that we can have. Now, once we know the pressure and temperature for the sample, total pressure and total temperature, then how can we estimate the maximum value of this one? This maximum value of the partial pressure of water vapor that it can be, that has to be the saturation pressure of water corresponding to the given temperature, that is the maximum pressure it can have, because any further increase in its pressure will lead to condensation, because we are actually pressurizing the water vapor by continuously adding mass to it and increasing the pressure of this one. As we keep on pressurizing, we know that then it will lead to the condensation process. So, the maximum pressure water vapor can have is the saturation pressure corresponding to the temperature. The relative humidity given by the symbol phi is defined as the ratio of the original partial pressure PWV, or maybe that it had at in a given sample, divided by this maximum partial pressure it can have at that particular temperature, or for a given temperature we can say that phi is given as phi PWV by saturation pressure corresponding to its temperature. Now, the other way we can write this one is, it can be written as omega divided by omega for the saturation condition. So, under this particular condition, let us say that the value of specific humidity is omega s. Omega s is the maximum value of specific humidity that this sample of moisture can reach. Now, how can you get the value of this omega s? Simply by replacing this partial pressure of water vapor in the previous expression with this maximum value. So, your omega s will be equal to 0.622 into P sat corresponding to the given temperature divided by P minus P sat corresponding to the given temperature. Now, relative humidity phi is defined as the mass of water vapor that we had in the original sample divided by the maximum mass of water vapor that we can have. Now, what is now using the definition of the specific humidity, we can say that this mass of water vapor is equal to omega into mass of dry air. Similarly, the denominator can be represented as omega s into mass of dry air, as the mass of dry air is remaining unchanged. So, this is equal to omega upon omega s. So, this relative humidity is nothing but the ratio of the specific humidity to the maximum possible value of specific humidity which is possible with this sample at the given temperature. That also corresponds to the saturated condition. Now, if we represent this one in terms of the PVT relationship, if we write the mass of water vapor divided by mass of water vapor maximum, then what this one will be? In the numerator we are going to have partial pressure of water vapor into V divided by R water vapor into T, as total volume and temperature remain the same. So, in the maximum condition it becomes P sat T into V divided by R water vapor into T. So, it then becomes partial pressure for water vapor by partial pressure at the given temperature. Therefore, phi can be represented in different possible ways. Relative humidity relates to the mass of water vapor present in a given sample divided by the maximum mass of water vapor that sample can hold, or the specific humidity to the maximum possible value of specific humidity, or the ratio of partial pressure of water vapor to the saturation pressure of water vapor at the given temperature. You can represent in whatever way that is comfortable to you, all will lead to the same result. Now, how can it relate these two quantities, the phi and omega? Omega, we already, for a given sample, let us say our specific humidity is omega and relative humidity is phi. Then what should be the relation? We know that omega is equal to 0.622 into P water vapor by P minus P water vapor. So, one possibility is that replace this P water vapor using the definition of phi, which will become phi into P sat corresponding to this temperature. Similarly, in the denominator also it becomes phi into P sat in terms of what at the given temperature. So, this is one possible relation. From the knowledge of relative humidity we can calculate specific humidity this way. Other possibility is that where we use the definition of phi and P water vapor we have. So, that partial pressure of water vapor let us substitute from the definition of omega. If we do that way, then it is going to be omega into total pressure divided by 0.622 plus omega into the saturation pressure corresponding to the given temperature. This way we can get another relation between the specific and relative humidities. The relative humidity is generally represented in percentage. It can vary from 0 to 1 or 0 to 100% because it is just a ratio, and in the denominator is always higher. So, the numerator can have the maximum value that is equal to the denominator, and that is why relative humidity can never be greater than 1. Now, for a given temperature, suppose the temperature of the sample increases, for a given sample the temperature increases, then what will be the effect on the specific humidity? Remember, specific humidity is a ratio of mass. As the temperature is changing, the mass of water vapor and mass of dry air, none of them are changing. Therefore, its specific humidity remains the same. What about relative humidity? Now, partial pressure for water vapor is the same because the masses are not changing, total pressure is also not changing. But as the temperature is increasing, the saturation pressure for a given temperature that also keeps on increasing, and therefore, relative humidity that keeps on decreasing. Therefore, when the temperature of a sample increases, its specific humidity remains constant, but relative humidity decreases. The reverse is true when the temperature decreases. What will be the effect of pressure? You think about that. I am leaving that to you. Next, I move to the term called the dry bulb temperature. Dry bulb temperature is nothing but the temperature of the air. The normal temperature that we can measure with a thermometer or by any temperature measuring device, that we generally call it dry bulb temperature. Here the term bulb refers to the bulb of a thermometer, mercury or whatever liquid filled thermometer that we use. From the bulb of that we use the term dry bulb temperature. So, the temperature that we are using, quite often this temperature is also written as temperature T dB, where dB referring to dry bulb. And what about the enthalpy? We are talking about a mixture of ideal gases. So, enthalpy for the air will be equal to the enthalpy for the dry air part plus enthalpy for the water vapor part. Enthalpy for the dry air part will be equal to mass of dry air into its specific enthalpy, and this will be equal to mass of water vapor into its specific enthalpy. Now, if we divide everything by the mass of dry air, then we get the specific enthalpy for the moist air, and this is represented as per unit mass of dry air. So, here the specific enthalpy for the moist air we are writing in terms of, we are not dividing it by the mass of the total sample, rather we are dividing by the mass of the dry air only, because the water vapor part may keep on changing, but the dry air part generally remains constant. So, the right hand side will be equal to H for dry air plus mass of water vapor by mass of dry air into H for water vapor, that is H for dry air plus omega into H for water vapor, because this bracketed term is nothing but the specific humidity. And we now know how to estimate these values. H for dry air, as you have seen, can be written as 1.005 into the dry bulb temperature. I am not putting the subscript, but you can also use the subscript dB, whereas for the water vapor part it will be omega into, for water vapor what we have written earlier, 2500.9 plus 1.82 into the dry bulb temperature. So, this way we can get the enthalpy of the specific enthalpy of the moist air sample. Remember, this H water vapor which we are writing in this particular form, we can also write this H water vapor is equal to the Hg for that given temperature. As we have seen, both of them nearly gives you the same value. So, this is the idea. Here the moist air part is omega. Suppose if we are taking 1 kg of dry air, then there will be omega kg of moisture and the total mass of the moisture will be 1 plus omega kg. So, we are having this as the total enthalpy, or I should say the specific enthalpy for the mixture. Just make a note of the unit that we are using here, kilojoule per kg of dry air. It is important to mention this dry air part in the suffix or in the denominator, because we are defining the specific enthalpy not in terms of per unit mass of the moist air, rather per unit mass of the dry air only. Let us quickly solve one problem just to see the application of this. Here we are talking about a room. The volume of the room is given, it is maintained at a temperature of 25 degree Celsius and 100 kilopascal, and its relative humidity is 75%. So, we have phi equal to 0.75, total pressure of the sample is 100 kilopascal and its temperature is 25 degree Celsius. I repeat, generally we use a symbol capital T to denote absolute temperature, but only when we are talking about air conditioning application, that is gas and water vapor mixture, then generally we keep on using capital T, but define everything in Celsius. Now, we have to define the partial pressure of dry air, the specific humidity, mass of dry air and the total enthalpy of dry air. So, we need to know the properties at this given temperature 25 degree Celsius. So, I have noted down the properties. Saturation pressure for this given temperature, where T is equal to 25 degree Celsius. From the saturation table we can get this to be equal to 3.1698 kilopascal, and Hg for water at this temperature of T equal to 25 degree Celsius is equal to 2546.5 kilojoule per kg. These values are taken from the table corresponding to the 25 degree Celsius. So, first we have to get the partial pressure of dry air. Then what is the partial pressure for water vapor? We know the relative humidity. So, use that definition. As per our definition, relative humidity is given as partial pressure for water vapor by P sat corresponding to the temperature, that is partial pressure for water vapor will be phi into P sat for that given temperature, that is 0.75 into P sat we have noted to be equal to 3.1698, that is coming to be 2.38 kilopascal. Hence, partial pressure for dry air will be equal to total pressure of the moisture sample minus partial pressure for water vapor, that is 100 minus 2.38, that is equal to 97.62 kilopascal. You can see the partial pressure for water vapor is such a small fraction, it is just about 2.3% of the total pressure, but still it can have a huge impact on the comfort level. So, the first answer that we have got. Now, we have to get the specific humidity. Specific humidity, we now know the relation. So, we can calculate this one to be equal to 0.622 into P for water vapor by P for dry air. So, it is putting this equal to 0.0152 kg per kg of dry air. You can write dA or you can write dry air. So, this is the specific humidity or humidity ratio. Now, to calculate the mass of dry air. To get the mass of dry air, we need to know the total volume. Total volume of the sample is given as 5 into 5 into 3, that is 25 into 3, that is 75 meter cube is the total volume of the room. And as we are talking about a mixture of two ideal gases, therefore, each of the gas is occupying the entire volume, both the dry air part and the water vapor part. So, if we apply the ideal gas equation of state on the dry air part, then we can write P dry air into volume will be equal to the mass of dry air into R for dry air into the temperature for this room. So, mass of dry air then should be equal to P dry air into V by R dry air into T. Now, partial pressure for the water vapor part we have just calculated to be equal to 97.62 into 10 to the power 3, total volume is 75. R for dry air is 287 that you can calculate, it is 287 joule per kg Kelvin, and temperature here of course we have to go for the absolute temperature because in the idealized equation of state we use absolute temperature. So, it is 25 plus 273, putting the numbers, the mass of dry air will be 85.61 kg. If you want to calculate mass of water vapor, how can we calculate that? You now know omega, you know mass of dry air, so it will be nothing but omega into mass of dry air, which is just 0.0152 times 85.61, which will be coming as 1.3 kgs. So, this is the third result that we are looking for, and finally, we have to get the total enthalpy of the dry air. Total enthalpy of not dry air, I want to calculate the total enthalpy of the air sample. Now, we know that specific enthalpy for the sample is defined as H for the dry air part plus omega into H for the water vapor part. For the dry air part, it is Cp into the dry bulb temperature, which is 25 degree Celsius in this case. Remember, here this T has to be in Celsius because we are actually writing T minus T reference, and T reference is 0 degree Celsius, plus omega into, here we can use the value of Hg for that given temperature, which we have noted down, or the other way we can also write this as Cp T into omega into that relation that we have used earlier, 2500 in the previous slide that we have written 2500.9 plus 1.82 T. I would request you to calculate this particular number because Hg I have already given to be 2546.5. You put the value of T equal to 25 here and check what values you are getting. I think you are going to get something like 2546.4, that is almost same. So, putting the values, Cp for air is 1.005 and T is in 25 degrees Celsius. So, you are going to get this to be equal to 63.8 kilojoule per kg of dry air. So, then total enthalpy will be equal to mass of dry air into this mass of dry air we have calculated, and specific enthalpy for the moisture sample also we have got, it is 5461.918 kilojoule is the total air for the total enthalpy for the sample. And if you are interested to get the total enthalpy for the dry air part, as I mistakenly typed, then that also you can calculate. Each dry air will be nothing but mass of dry air into Cp into T. Similarly, you can also calculate the enthalpy content of the water vapor part. So, we have now made use of the concept of relative and specific humidities. Now, let us move to another concept known as the dew point temperature. Let us say we have a fixed quantity of moist air at a given pressure and temperature. Now, if the total pressure of the system, let us say is P, mass of dry air and mass of water vapor, these are given. If these two are given, then from this we know the value of omega, and also if we know the omega, at least to start with, you also know the value of phi, because phi will be equal to the partial pressure for this water vapor sample divided by P sat corresponding to this temperature. Now, as the masses, we are not going to change the mass, and as we are not going to change the mass, so partial pressure for, and also the total pressure remaining constant, therefore, the partial pressure for the dry air part and partial pressure for the water vapor part, they also remains the same. So, I repeat, we have a sample of a fixed quantity of moist air that we have, which contains some fixed quantity of dry air and water vapor. We are maintaining the pressure and also the masses of both constituents the same, and therefore, its specific humidity and also the partial pressure for both the components remain constant. Now, we start lowering the temperature. So, this is the point where we are initially present, this is the temperature. So, initially the substance is actually superheated corresponding to its water vapor. Here this graph we are plotting this TS diagram only for the water vapor part. So, for the given pressure, that is given partial pressure of the water vapor, and for the given temperature it is actually superheated. Now, maintaining system pressure and the masses the same, we just keep on lowering the temperature. As the temperature is getting lowered, it will follow the isotherm just shown here, something like this. So, initial temperature say is T1 like shown here, and here we have plotted the isotherm which corresponds to this P water vapor. As it keeps on decreasing, it is becoming increasingly closer to the saturated vapor line, and then at certain temperature it will reach this point number 2, where it actually reaches the saturated vapor point. Now, as you are moving from point 1 to point 2, what is happening to the specific and relative humidities? Specific humidity remains constant because the masses are not changing. So, specific humidity is a constant. What about the relative humidity? During this process, as we are moving from 1 to 2, the temperature is decreasing. Therefore, the saturation pressure corresponding to the temperature, that is also decreasing, but the partial pressure for water vapor, that remains constant, and therefore, your relative humidity, that in just look at the expression here, the numerator is constant, but the denominator is decreasing. So, the relative humidity keeps on increasing, and when we reach this point number 2, the relative humidity becomes 100%. That is, the mixture becomes saturated by whatever moisture originally it had, by that only. We have just lowered the temperature, and by continuously lowering the temperature we have reached a point where the mixture of the moisture is getting saturated only by the water vapor content that it originally had. This particular temperature, this temperature point T2 is known as the dew point temperature. I repeat, this temperature is known as the dew point temperature, TDP. We can write TDP, or we can also write TDPT, whatever we would like to represent this dew point temperature. Therefore, how can we calculate this if we know the partial pressure for water vapor? This has to be the saturation temperature corresponding to the partial pressure for water vapor, and partial pressure for water vapor we can calculate from the expression for this relative humidity that we originally know. So, for a given relative humidity we can easily calculate the value of the dew point temperature. Now, what is the physical significance of this? Just think, if we lower the temperature any further, then what will happen? If we lower the temperature any further, then at even lower temperature it will not be able to hold that much amount of moisture. So, some moisture will get separated from the moisture sample, and it will condense, it will get converted to liquid water, and it will get deposited. And you definitely have seen the formation of dew, the formation of mist, and that is just relevant to this. Just take a say a cold can of some soft drinks from the refrigerator, immediately you will find, take it outside, and immediately you will find that lots of moisture has got deposited on the outer wall of that can. That is happening because the temperature of the can surface is lower than the dew point temperature of the surrounding air, because it was inside the refrigerator. So, it is at a very low temperature, and therefore, the moisture which was there present in the surrounding air, that gets condensed and gets deposited on the surface of that can. So, the concept of dew point temperature is very important from air conditioning application, as we shall be seeing in the next lecture. Next, we move to something known as the adiabatic saturation. Now, the idea of dew point temperature is very important, as I have mentioned, but the next question is, how can we calculate the value of the dew point temperature? One option is to measure the partial pressure for water vapor, because if we know the partial pressure for water vapor, then from the temperature we can calculate the saturation temperature, and from that saturation pressure rather, and then from that ratio we can calculate the relative humidity. And also using that partial pressure of water vapor, we can calculate the dew point temperature directly, but that may not be the easiest of procedure. For that purpose, we can often go for this particular arrangement that is shown here, which is known as a setup for getting adiabatic saturation. Here, a quantity of air with initial temperature T1, specific humidity omega 1 and relative humidity phi 1 is allowed to enter a long adiabatic duct, just like shown here. In this duct, we are having liquid water stored up to certain level. If the water is initially unsaturated, then if the air is initially unsaturated, then when it flows over the water surface, it will keep on picking up water vapor from this pool of water, and as it picks up liquid water, then its omega that keeps on increasing. However, this water that is stored here, shown by the pink, that is stored in the liquid condition. So, if water molecules has to go to the air side, then it has to get converted to vapor, and therefore, it needs that latent heat of vaporization. That latent heat of vaporization, as this duct is ideally insulated, it is perfectly adiabatic, then this latent heat of vaporization will be coming from the body of this air only and also from this liquid water. So, the temperature of air and liquid water both keeps on decreasing, and finally, it is, if the channel is sufficiently long, we can expect that the outlet condition, we are going to get a 100% saturated mixture, that is, it will come out with a relative humidity of 100%, and omega 2 also will be greater than omega 1, and T2 will be, it will be lower than T1 or higher than T1. It will be lower than T1 because both water and air has lost energy in order to supply that latent heat of evaporation to the water vapor, and therefore, the temperature will fall, specific humidity will increase, while the mass of dry air remains the same, and relative humidity finally reaches 100%. Now, of course, some quantity of water is getting lost from the liquid side. So, you need to make up for that liquid water at that same temperature T2. Now, the temperature T2 at which it is coming out, this temperature is often known as the adiabatic saturation temperature, and if we represent the process on a TS plane, this is the point from where we are starting. Remember, we are not following any constant temperature or constant pressure process, because temperature is decreasing, whereas the pressure of our water vapor will increase as more and more mass of water vapor is getting added to this. So, we shall be finally reaching a point like this. This is your dew point temperature, and this point number 2 that we are reaching, that is called the adiabatic saturation temperature. Now, how can we identify using this adiabatic saturation temperature T2, we can actually get a measure of the value of this omega 1. This entire apparatus, our objective is to get the value of this omega 1, and that we can obtain from the measured value of this temperature, initial temperature T1, and finally obtained adiabatic saturation temperature T2. From the dew point temperature also we can get the value of omega 1, but that is more difficult to get, and therefore, we can go for this particular arrangement, which is called the adiabatic saturation temperature. Now, how can we get the value of omega 1 here? Remember, omega 2 we can also measure, but generally that is not required, because if we know T2, we know phi 2 is equal to 100%. So, omega 2 we can easily get. Now, we have to get omega 1. If we perform a mass balance for the dry air part, so m dot dry air at 1 is equal to m dot dry air at 2, because there is no change in the dry air. So, let us say we call it m dot dry air. Now, we perform mass balance for water vapor side. So, m dot water vapor at point number 1 plus m dot f, which we are adding from this side. Here we are adding m dot f amount of liquid water at temperature T2, should be equal to m dot water vapor at point number 2. Now, using the concept of omega 1 and omega 2, we can say that this m dot water vapor can be written as m dot water vapor at 1 can be written as omega 1 into m dot dry air plus m dot f, should be equal to omega 2 into m dot dry air. That is, from there m dot f, the mass of makeup liquid that we have to supply, is equal to omega 2 minus omega 1 into m dot dry air. Now, you have to perform an energy balance. As there is no other source of energy and this chamber is insulated, so we can write E dot in has to be equal to E dot out. Now, how much energy we are adding? The amount of energy we are giving initially is m dot dry air into H1, H1 is the specific enthalpy of the moist air sample at state 1, plus m dot f into HF2, HF2 refers to HF at temperature T2, should be equal to m dot dry air into H2. Now, m dot dry air into, okay, let us divide everything by m dot dry air. So, we have H1 plus m dot f is omega 2 minus omega 1 into m dot dry air divided by m dot dry air into HF2 is equal to H2. Separating that out, removing m dot dry air, we have H1 plus omega 2 minus omega 1 into HF2 is equal to H2. Let me repeat this one here. So, we have H1 plus omega 2 minus omega 1 into HF2 to be equal to H2. Now, what is H1? For the dry air part, it is Cp for the dry air, let us say Cp dry air into T1 plus for the water vapor side we can write in Cp form or we can write in Hg form. So, it is Hg1 into omega 1, that is your H1 plus omega 2 minus omega 1 into HF2, and your H2 will be equal to Cp for the dry air into T2 plus omega 2 into Hg2, where Hg2 is Hg at temperature T2. So, if we separate out now the omega 1 part, so we have omega 1 into Hg1 minus Hg2 minus omega 1 into HF2 is equal to Cp for the dry air into T2 minus T1 plus omega 2 into Hg2 minus HF2. So, omega 1 now becomes then, so inside the bracket if we combine this, we have Hg1 minus Hg2 plus HF2 omega 2 into HF2 Hg2 minus HF2 is what? That is nothing but HFG at 2. Here I have written one term extra, Hg1 minus, sorry, omega 1 Hg1 minus omega 1 HF2. So, that term I wrote wrongly, fine. Then it becomes even shorter, Hg1 minus HF2, which gives you final value of omega 1 to be equal to Cp for dry air, which is nothing but 1.005 into the change in temperature, T1 and T2 both are known quantities, plus omega 2 into HFG2 by Hg1 minus HF2. Now, what are the parameters that we have to measure? We have to measure T1, the initial temperature, and once we know T1, then your Hg1 is Hg corresponding to this T1. We have to measure T2, the final temperature, and once you measure final temperature, then HF2 is HF corresponding to this T2, and HFG2 is HFG corresponding to this T2. So, we know the properties. Cp for dry air is 1.005 kilojoule per kg, we know, but what about omega 2? How we can get omega 2? Remember, omega 2 corresponds to saturated air, that is the maximum specific humidity it can have at this temperature T2. So, omega 2 is nothing but 0.622 into saturation pressure corresponding to T2 divided by P minus P sat corresponding to T2, as phi is equal to 1 or as our phi 2 is equal to 1. P sat corresponding to T2, that also we can get. So, we just have to measure the two temperatures T1 and T2. The T1 is the initial temperature of the sample, T2 is the final temperature once it comes out after becoming saturated under this adiabatic condition, the adiabatic saturation temperature basically, and then by getting certain property values corresponding to this temperature T1 and T2, we are getting the measure of initial specific humidity, that is omega 1. So, this is a very interesting arrangement, this adiabatic saturation condition, by which we can easily measure the specific humidity, and once we know specific humidity, we can calculate anything. We can calculate relative humidity, we can calculate the partial pressure of water vapor, we can calculate enthalpy and also the dew point temperature. but generally we need to provide a very long duct and a sufficient amount of time to get this process done. Also getting ideally insulated condition, perfectly adiabatic process may not be very practicable. So, quite often we go for a much simpler arrangement. We take a thermometer and we cover the bulb of the thermometer by a piece of cotton and or some wick, and the arrangement is such that the wick is partially immersed into a pool of liquid water, so that it always remains saturated with water. Then as air or whatever medium for which you want to measure the temperature, it is allowed to flow through, it will pick up certain amount of moisture from this, and as it passes over the wick we can expect it to be saturated corresponding, and once it picks up the water vapor from the wick, the corresponding latent heat has to be provided from the bulb of the thermometer, and hence whatever temperature we get, that we call the wet bulb temperature. This wet bulb temperature practical is may not be exactly equal to the adiabatic saturation temperature, but for most of the practical purposes we take this wet bulb temperature to be equal to the temperature for adiabatic saturation. So, we now know that there are three temperatures that we talk about. One is the dry bulb temperature, one is the dew point temperature, and finally is the wet bulb temperature. These are the three temperatures that we commonly keep on using in practice. The dry bulb temperature is the ordinary temperature only, which you can measure using any temperature measuring device. For measuring wet bulb temperature, we have to get an arrangement something like this: the bulb of the thermometer covered by a wet wick, and the wick also has to be in contact with liquid water always. And the dew point temperature refers to the temperature at which the moisture sample becomes saturated by its own moisture content. So, to finish with, I have a very small numerical example where I shall be using the concept of both dry and wet bulb temperature. So, we are having atmospheric air at this pressure of 101 kilopascal, and the dry bulb temperature is 25 degrees Celsius and wet bulb temperature is 15 degrees Celsius. So, you have to measure specific and relative humidities and the enthalpy of air. So, as we know the two temperatures, the saturation pressure corresponding to 15 degrees Celsius is 1.7057 kilopascal, and corresponding to 25 degrees Celsius it is 3.1698 kilopascal. These two properties we have taken from the table, and once we have this, we basically can have everything, because we know that omega 2 will become equal to 0.622 into P sat corresponding to your T2. T2 means which one? T2 is the wet bulb temperature. So, it is into 1.7057 divided total pressure is 101 minus 1.7057, it is coming to be 0.01065. So, you know omega 2. So, omega 1 we can calculate just like we have calculated from, we got the formula from here. So, we have Cp for air to be equal to 1.005 into change in temperature, T1 is 25, T2 is 15, and if we go back, we have omega 2 into HFG2 plus omega 2 is 0.01065 into HFG corresponding to 15 degrees Celsius, which I have not noted, you can take the value, and then we have Hg1 minus Hf2. So, Hg corresponding to 25 degrees Celsius minus Hf2, that is Hf corresponding to this 15 degrees Celsius. Have these enthalpy values and from the table and do the calculation, your omega 1 should be something like 0.00653. Then how to calculate phi from there? We know the relation between phi and omega, there are several ways you can calculate phi from this. Just check it out, your phi will be something like 33.2%. And once you know this, you also know how to calculate the total enthalpy or at least the specific enthalpy for this mixture. Try to calculate this one your own. So, that takes us to the end of our discussion for the day, where we have talked about the atmospheric and dry air, the concept of dry air and moist air, concept of specific and relative humidities, dry bulb and wet bulb temperatures, dew point temperatures, and finally, we have talked about the adiabatic saturation, which is also associated with this concept of wet bulb temperature. Please rehearse these concepts carefully, because in next lecture I am going to talk about something known as the psychrometric chart, which allows us to calculate or get the values of different parameters which we have defined here directly without doing any kind of calculation. Of course, we can get all these parameters by calculation, but we can also get them directly from the psychrometric chart, and then we shall be trying to plot a few air conditioning processes on the psychrometric chart to get into more detailed about air conditioning calculations. Thank you very much.